This is AP Calculus AB. We're looking at Notes 1.3, Graphical and Analytical Connections using the properties of limits. Now, these properties for limits are super intuitive, common sense, and no-brainers. Suppose the limit of f of x as x approaches a equals capital L, and the limit of g of x as x approaches a is capital M. Find each of the following limits in terms of L and M. That means we're going to have L's and M's in our answers. So this first property, it's giving you part of the property, we're going to finish the property. If you have a limit as x approaches a, and your argument is multiple terms, multiple functions, if you wanted, you could simply write this as the limit as x approaches a of the first function plus the limit of g of x as x approaches a. Now we know from up here that this limit is L and that this limit is M. So this is simply L plus M. Same works with subtraction. If you are subtracting in your argument, like so, if you wanted to, sometimes it's easier to break it apart as the limit of the first function minus the limit of the second function. You evaluate each of those limits the way that you would normally do it. And once again, we know that this is approaching L because we're told that up here, and this limit is approaching M because we're told that up here. 3 and 4 are division and multiplication. If you have a limit and your argument is division, you can take the limit of the numerator and divide that by the limit of the denominator. Super intuitive, and we said that f was approaching L as x approaches a, and g was approaching M as x approaches a. If you are multiplying your arguments, you could write that as two limits, the limit of your first factor times the limit of your second factor, which in this case is L times M. Number 5, this one is perhaps the most useful. Perhaps. C here is a constant. It's a number, it's a coefficient, it's a number of multiplying by the function. If you want, you can pull the constant out to the front of the limit. We will be using this all the time. We're going to choose to do this all the time because it's going to make things easier for our brains. So this limit, as it says in the directions, is approaching L. So we just have C times L. Number 6, if you have an argument that is raised to an exponent, if you want, you can find the limit of the argument and then raise the answer to the exponent. And then lastly, as x approaches a, what does y approach if your function is c? Well, it's just c. And the reason is that c means it's a horizontal line. It's a constant function. So no matter which a value you pick, if you're approaching a, no matter where it is, from the left or the right, well, the y value is always the same thing. It's always c. So that's why this here is going to be the same as that constant. Let's check out some examples. Find each limit. If a limit does not exist, state why. Number 1, we have this limit, and it's a little complicated. Boy, I really crammed these in here, didn't I? Oh well, what are you going to do? Live and learn. So number 1, I'm going to rewrite this as the limit as x approaches -1. I'll tell you what, let me change that a little bit. 2 times the limit as x approaches -1 of f of x minus 3 times the limit of g of x as x approaches -1. Let me just break down for you what just happened. This argument has subtraction, so I broke it apart. So we got this limit minus this limit. This first function has a coefficient, so I brought it out to the front. The second one also has a coefficient, I brought it out to the front. So this part here is here, and this part here is written here. Now looking at our picture, we're going to have 2 times this limit, we're going to have 3 times this limit. So this is the graph of f. As x approaches -1, here's -1, what is the y approaching from both sides? Well, it looks like it's approaching -6. Here's g of x. What's the limit of g of x as x approaches -1? Well, here's -1. It looks like it's approaching -1 on both sides. Then it's just some algebra. 2 times -6 is -12. Let's subtract 3 times the -1 is a +3. So this is -9. Number 2, this is simply subtraction. So it's going to be the limit of f of x as x approaches -3 minus the limit of g of x as x approaches -3. So here's function f. As x approaches -3, here's -3, y is getting closer to -2. Notice the y value is undefined, but that's cool. It doesn't matter. It doesn't have to be defined. As you approach from both sides of -2, it's approaching the same. I'm sorry. As you approach from both sides of -3, the y is approaching -2. What about function g at -3? Well, we got a problem here. Here's -3 for this function. If you approach from the left, it's approaching infinity. If you approach from the right, it's approaching -infinity. Those don't agree and they're not a number. So this does not exist. In a fight between a subtract 2, a -2 and a subtract does not exist wins every time. Just as a note here, g of x has a vertical asymptote at x equals -3. That's why this doesn't exist. Number three, we could rewrite as -2 times the limit of f of x as x approaches 6 over the limit of g of x as x approaches 6. So this is going to be equal to -2 times the limit over some limit. And if you look at our picture, as x approaches 6 for function f, here's 6. As you approach from either side, it's approaching this y value of -4. Function g, as x approaches 6, it's approaching the y value of 6. So that's going to be 8 over 6, which is 4/3. Number 4, excuse me, pardon me. We could write this as the limit as x approaches -2 of f of x. And then when we find that, we can just square the answer. So if we look at our graph down here, as x approaches -2, from both sides, looks like y is approaching -5. And we square that, and we're going to get 25. Last one, number 5. We could rewrite this as the limit. Actually, I'm not going to rewrite it at all. It's going to leave this as 2 times. What does g of x approach as x approaches 2 from the right? So here's 2. If you approach from the left, it's approaching 1. If you approach from the right, it's approaching 6. We're approaching from the right, so that should be a 6. This is the square root of 12. You could simplify this and make it 2 square roots of 3, but you don't need to. Because once again, in AP Calculus, unless it's a multiple choice, we don't need to simplify anything. Let's check out a little more complicated examples. Number 6 is kind of important. Number 7 is monumentally important. Number 6, supposed to find this limit. Well, to find this limit, we are definitely going to want to replace g of x with what it's equal to, which is this. And we're going to want to replace g of negative 2 with what it's equal to, which is this, replacing the x with a negative 2. So we have 2 times g of x, which is 3x plus 2. And then we add to that g of negative 2. If we put a negative 2 into this, we're going to get 3 times negative 2 plus 2. And then the denominator is just x. Please note, we cannot use direct substitution right now. If we were to put 0 into this, the top would be something, who knows. The bottom would be 0, which would make this undefined. So we can't substitute right now. We're going to have to simplify this. To simplify it, let's do some algebra in the numerator. 2 times 3x is 6x. 2 times 2 is 4. And then up here, 2 times negative 3 is negative 6. And then we got a plus 2. If we combine like terms, plus 4 and a minus 6 and a plus 2, that gives us 0. So on the top we have 6x plus 0, which is 6x. And the bottom we had x all along. Please note before I continue, we have not evaluated the limit yet. So we have to keep writing limit notation. Once we evaluate the limit, and in lots of cases it means we're going to be substituting the 0 in for the x's, then we can stop writing the limit. We can divide the top and bottom by x. What's that mean that happened? It means there was a hole. Now to evaluate the limit, we're going to put 0 in for our x's. Oh, we don't have any x's, so that must mean this limit is approaching 6. This is an example once you get to this point here. Let me write this 0 a little bit better. An example of that last property that we had right here. The limit of a constant as x approaches a number is whatever that constant is. That's what just happened. All right, this is it, number 7. You don't know it yet. This right here is calculus. This is the most important limit that you will ever do. You will use this limit hundreds, if not thousands of times in this class. In fact, this is the definition of derivative, and we will get to that later, but this is so important. This is the limit of the difference quotient. Not a difference quotient, the difference quotient. Lovely, isn't it? So here's what we got. We got the limit as h approaches 0 of f of x plus h minus f of x over h. This needs memorized, folks. I'll give you the context later, but go ahead and memorize it now. So here's what we're supposed to do. We're supposed to take this limit and we are supposed to, in this first position, replace function f, I should say use function f, and replace the x values with an x plus h. So that's what's going to go here. Then we're going to subtract from that just the original function. Let me write down the original function first because that's easier. The original function f of x, which goes here, is simply this function here. 2x squared minus 3x plus 4. Yes, you need this subtraction sign. And what I really want to emphasize, you need these brackets because we've got to distribute the subtraction. Here, we're going to use this function, but replace the x's with x plus h. So we have 2 times x plus h, quantity squared, minus 3 times x plus h, and then plus 4. This is this, and this is this. Now, we would like to just evaluate the limit, be done, but we can't substitute in right now, so we put a 0 in for h. We're going to be dividing by 0. It's going to be undefined. So we have no choice but to multiply all this stuff out, and hopefully we can factor out an h so we can cancel it from the bottom. Exciting, isn't it? I actually am excited. I love this. So let's see. What is the quantity of x plus h squared, that binomial? Well, that's going to give us x squared plus 2hx plus h squared. We're multiplying two binomials together, you're going to get a trinomial. If I distribute this minus 3, I get minus 3x minus 3h. Can't forget this plus 4. Students often forget that plus 4. Distribute this minus, I'm going to get a minus 2x squared plus 3x minus 4. Now we're getting closer. We don't want any parentheses up here. We want to be able to combine like terms. So I'm going to distribute this too. I'm sorry, made a mistake right here. This is not squared anymore. We already squared it. That should not be a squared. We have not evaluated the limit yet, so we're still using limit notation. We're going to have 2x squared plus 4hx plus 2h minus 3x minus 3h plus 4 minus 2x squared plus 3x minus 4. Let the blood bath begin. We got a positive 2x squared. We got a negative 2x squared. We got a minus 3x. We got a plus 3x. We got a plus 4. We got a minus 4. And bloodbath. Now we have the limit as h approaches 0. Terms we have left in the numerator is 4hx plus 2h minus 3h, and the denominator is just an h. So what has just happened? This has enabled us to factor an h out of the numerator, because every term has an h in it. Leaving us with 4x plus 2 minus 3 over h. Cancel an h from the top and the bottom. We have to continue to write limit notation because we have not evaluated the limit. If your argument is more than one term, I think I made a mistake here. Hold on, wait for it. Oh, bother. I'm so sorry. I don't know if I said it right. I certainly didn't write it right. Oh, I see. I had this squared up here and then I erased it. So, yeah, squared shouldn't have been there, but it should have been h squared. So, here's the beauty of me making this mistake. I mean, it wasn't intentional. If you find your mistake and you're showing your work correctly, it's easy to fix. So when I distribute this, it's going to be h squared. And then like bring that term down, it's squared. I factor an h out. It's going to be minus 2 plus 2h minus 3. There we go. 1,000 pardons. Now to evaluate the limit, we're going to put 0 in for all of the h's. Once you do that, you stop writing limit notation. And we end up with this limit being 4x minus 3. Someday, hopefully soon, I will explain to you what this actually means. And it is wet.